diuruskannya dengan Bank Mandiri khusus untuk ngurusin taspen, jadi Mandiri Taspen namanya teh.
Iya.
Jadi nanti begitu dapat SK kita boleh lapor ke Bank Mandiri Taspen, diuruskan mereka gitu.
Iya.
Sampai ada uang atau gaji bulanannya juga oleh mereka.
Ya, emang CGB kapan itu apa purna tugasnya itu?
Saya sih tanggal lahirnya 6 Desember. Tapi saya nggak tahu apakah 6 Desember SK-nya itu 6 Desember atau terhitung Januari gitu. Belum tahu tuh Mas Seb.
Iya.
Tapi kemarin Bu Ius tanya ke SDM belum ada sih.
SK-nya ya?
Iya, SK-nya.
Oke, Bapak Ibu, sepertinya Prof. Naresh sudah hadir.
Mangga, Bu Amel, saya nggak
Okay. Good afternoon. Okay,
Good afternoon.
Good afternoon, Prof. Naresh.
Is it selamat sore?
Ya, selamat sore. Okay, selamat sore in Australia. And
Australia, it's evening now, 6:40.
Oh, evening. Okay.
Yeah.
Good evening, so.
Right.
Okay, Prof. Naresh, I apologize for the delay because
That's all right. There's no. I think Vidya told me about it, so that's okay.
Yeah, because we have another visiting professor class from Gifu University, so
That's okay.
and using this account, so we.
All right. Okay.
Okay. Selamat, Prof. Naresh. I will open this session.
Yeah. I can come back in a couple of minutes if you like. I can just mute myself and.
Okay.
When you're all ready, I can start later.
Maybe we wait for 3 minutes, maybe? Is it okay?
No worries. Yeah,
Okay. Thank you, Prof. Okay.
Yeah.
Because Bu Vidya has another agenda. So, okay. Today I will be the moderator.
Okay, no problem.
Okay. Ya, selamat siang, Prof. Asep, Bu Gebi, and there is Bu Fitri.
Selamat siang. Good evening, Prof. Naresh. Nice to meet you again.
Good to see you again.
Yeah.
I like your background. It's very nice in your video.
Thank you.
Very neat and tidy.
In the house, Prof. Asep, or in the lab?
Yes, this is my small lab at my house, Prof.
Oh.
Okay. That's good.
Okay.
My majoring research about essential oil.
Oh yeah, okay.
Yeah.
That's
and
good.
I try to learn more about the aromatherapy now.
Oh yeah,
and synthesis some compound derivative from essential oil.
Yes. No, they are very popular in Australia. Essential oils and aromatherapy is very common.
Yeah, also in Indonesia now. Yeah.
Okay.
Many people use essential oil for the aromatherapy.
Yes, that's right. And some of them have very calming effect. They calm people down because everybody is stressed from COVID, so need something to calm it down.
Yeah, can relax, yeah, Prof.
Yeah, sleep well, more relaxed. Yeah. Our body.
That's right. We are doing some work on tea tree oil as well.
Oh yeah.
So that has antibacterial properties. So we are working with a company who is selling the sanitization based on tea tree oil.
Yeah. With the herb smell.
Yeah, that's right.
All right, Prof. It's already 2:45. Shall we start?
Yep.
Okay, thank you very much.
All
right. Hello everyone, welcome back to this class in organic chemistry. Especially today we will discuss related with the monofunctional structure and reactivity of monofunctional compounds, and with the topic alkane. And my name is Amel, and it's my pleasure today to be a moderator for this session. And without any further ado, Prof. Naresh, I think we already delay for 6 minutes.
Yep. All right.
Yeah.
I'll start sharing my screen.
Yeah. So this time is yours, please.
Thank you. Okay, I'll just make it a bigger screen, and I get a pen which is already here. So I can use that. I'll just check. I can use my pen.
Okay.
And yeah, I got it.
Yeah.
Okay, so I'm gonna talk about monofunctional compound in this series of lectures. I think I got quite a few lectures to give. So I have 3 topics in mind. One is carbonyl compounds. Second one is alkenes, and the third one will be alkynes. So I'm gonna start with carbonyl compounds.
Right.
Only going to work on the monofunctional compounds. In the other lecture, when we talked about bifunctional compounds, we talked about compounds which had 2 carbonyl groups. But now we're going to talk about just 1 carbonyl group, because this is I think a first year class and they don't have that background. So we're going to start with something very simple. Okay, so if I just go to the next slide. What are carbonyl compounds? You might ask me. Carbonyl compounds are compounds which contain a carbonyl group, and carbonyl group is represented by C double bond O. Okay, and the carbonyl group can be present in 3 forms indicated in 3 structures here. They all have carbonyl group, but the difference between the 3 structures is the carbonyl group here has a carbon attached on one side and it has a hydrogen attached on the other side. So that's very, very important. When there's a hydrogen attached onto the carbonyl and a carbon group attached to the carbonyl is called as an aldehyde. And when the carbonyl carbon has 2 carbon groups attached to it, is called as a ketone. And the carboxylic acid is when the carbonyl carbon has an OH functionality. This is called as a carboxylic acid. So that means the group that is present is C double bond OH. You can also get derivatives of carboxylic acids as well, and we'll look at that in a second as well. But the first thing we're going to look at is aldehydes and ketones and the carboxylic acid derivatives after that. Let's just give you some examples to show that why the aldehyde compound. So we are talking about aldehydes now, where you have a carbonyl and a hydrogen attached to it. And these compounds are very interesting compounds. And just now we were talking about essential oils, but also a lot of the smelly chemicals as well as compounds which give the nice flavor, they have aldehyde group present in it. For example, this molecule is called vanillin and it comes from vanilla beans. So those of you who have a vanilla milkshake at McDonald's, the vanilla flavor comes from this chemical over here. And same is this aldehyde here, which is the benzene attached to a COH. And this comes from almonds. So the almond flavor you feel is because of this benzaldehyde compound. Cinnamaldehyde has this again aldehyde group present in it, and that is present in cinnamon. And cinnamon is used a lot in Asian cooking. And this is the characteristic, the flavor we get of cinnamon is because of this chemical. And a simple molecule, CH3COH, acetaldehyde, it's a quite unpleasant compound. And this is the compound which gives people the unpleasant feeling when they drink a lot of alcohol, because body converts the alcohol into acetaldehyde before it excretes it out. And the simplest aldehyde compound, which has 2 hydrogen attached to it, is called as a formaldehyde, and it is a highly toxic compound. And this chemical is used for preserving animal tissue. So if you go to biology lab and you see the specimens stored in it, that specimens are typically stored in formaldehyde. And ketones are also very interesting, important compounds. So ketones are where you got one carbon and the other carbon on the other side of the carbonyl. This compound here called methyl isobutyl ketone, we'll see the nomenclature of the carbonyl compounds in a minute. But for the time being, this compound called methyl isobutyl, because this group here is a methyl group, and this group here is a 4-carbon group here over this side. And this is an isobutyl. That's why we call it a methyl isobutyl ketone. And that is chemical that is used a lot in industry in paints and coatings. Similarly, this compound here, which got a ketone group, it comes from raspberry ketones. You know, the red raspberries we get in the market. If you extract it out, you will get this compound. And it is used in perfumes, cosmetics, and food additive as well. And acetone is also the simple carbonyl ketone, is a commonly used solvent. And sometimes the nail polish remover which we use is actually acetone solvent. And also many natural compounds which smell very nice, they also have this ketone functionality present in it. And the third example of the carbonyl compounds I gave you earlier were carboxylic acids. And there are many carboxylic acids which are present in nature, and they are very, very useful for biology as well as industry. A very simple acid, acetic acid, you would have all smelled it one way or the other. That's the active constituent of vinegar. And vinegar is used in cooking and pickles. You know, the soury taste we get in pickles is from acetic acid or vinegar. Hexanoic acid, this is a 6-carbon carboxylic acid. And the fatty acids, long chain fatty acids or short chain fatty acids, they all have carboxylic acids. You'll be surprised that aspirin, the one we take for headaches and fever, also has a carboxylic acid group present in the molecule. And so is benzoic acid. Benzoic acid is a very common preservative. So the chances are when you drink orange juice, you take any food which has preservative, the chances are benzoic acid will be present in it. It's a very, very common preservative. Even bread has benzoic acid added to it as a preservative. Tryptophan is like an amino acids, and as you will know that there are many amino acids which are essential biologically for us. So carboxylic acid is a very important functionality. And I also earlier mentioned that carboxylic acids can have derivatives as well. And we will be looking at the carboxylic acid derivative as a separate lecture later on. But if you replace this hydrogen in the carboxylic acid with a carbon group, it becomes an ester. And if you link 2 of these carboxylic acids together, you will get an N-hydride. So you can imagine that if you have 2 carboxylic acids sitting side by side and you remove a water molecule from it, you will get the corresponding N-hydride compound. So this is one carboxylic acid. And if I write another carboxylic acid next to it, hydrogen, oxygen, sorry, excuse me, the writing, C double bond, C double bond, oxygen here. And then I put another R group on this side. And if I remove water from this compound, say we remove OH, that's like water is removed, you will get the corresponding N-hydride compound. Similarly, acid halides, COCl or COBr, they are also carboxylic acid derivatives. And amides, the primary amide, the secondary amide, and the tertiary amides, they're all derivatives of carboxylic acid. So this is an introduction to the three different types of carbonyl compounds that are there. So the question you might ask is, how do we name these carbonyl compounds? I'm going to give you a systematic name and as well as a common name for some of these compounds. The simplest aldehyde, as we looked at earlier slide, was a formaldehyde compound, we said. And if it was CH3COH, we said that was an acetaldehyde. But these are not the scientific names. They're like common names. The scientific name or the systematic name for these aldehydes has an Al present at the end. If a name has an Al present at the end, that means it is an aldehyde compound. And methanol here stands for one carbon, because if you look the corresponding hydrocarbon corresponding to one carbon is methane. And methane, as you know, has carbon with the 4 hydrogens attached to it. This is called as a methane. That's the simplest hydrocarbon that is possible. So this methanol indicates that it is a one carbon compound, aldehyde compound. That's why the name is methanol. And if you take it to 2 carbons, then it becomes ethane, and Al at the end becomes ethanol. And if you have a substituent present in the carbon chain, which is attached to the carbonyl group, then the nomenclature becomes carbonyl is carbon is always 1, and this carbon is 2, and this carbon is 3. So then the bromine group is present at the 2 carbon, and the carbon chain here is a 3 carbon chain, and 3 carbon chain is a propane. So that means this molecule will be 2-bromopropanol, 2-bromopropanol, because it's a 3 carbon aldehyde. And common name is alpha-bromopropanaldehyde. And the alpha comes from the Greek letter, which says that the first alphabet in Greek letter is alpha. And this carbon here is alpha carbon in Greek alphabet. And that's why this compound is called commonly alpha-bromopropanaldehyde. And the same applies to the other substituted compounds. Like in this case here, if you look at the carbon chain that is present, that is 4 carbon. So it's going to be a butanol. And it has a chloro substituent present on 1, 2, 3 positions. So it becomes 3-chlorobutanol. And the common name for that is beta-chloro, because this is alpha in Greek alphabet. This is beta in the next alphabet in Greek alphabet. So that's why it's called as common name beta-chlorobutylaldehyde, but the scientific name is 3-chlorobutanol. And same with the 3-methylbutanol, because the group present at the 3 position now is a methyl group. What if you got 2 aldehyde present in a molecule? Then what you do is look at the carbon chain you have. So you got 1, 2, you got 3, 4, 5, and then you got 6. So it's a 6 carbon chain molecule. And if it's a 6 carbon chain molecule, it is a hexane, but it got 2 aldehydes in it. So that's why it becomes hexane diol. That means 2 aldehyde present in the same molecule. And if you have a cyclic compound, then it is quite easy, because the cyclic hydrocarbon here is cyclohexane, and the aldehyde group is carbaldehyde is called. And then the methyl group is present at the 2 positions. So if we call that as cyclohexane ring, this is the 1 position and this is the 2 position. And it is called as 2-methyl cyclohexane carbaldehyde. And the geometry or around this 2 substituent here is trans, because one group is up, another group is down. So the geometry is trans. So that's why it's called as trans 2-methyl cyclohexane carbaldehyde. And we talked about this already. This is called benzaldehyde. but the systematic name for that is benzene carbaldehyde. Yeah, that's the scientific name and systematic name. Okay, if you need to work it out, which one should get priority in terms of nomenclature? If a structure has more than one functional group present, then you need to find out which group is the higher priority and which group is the lower priority when you're naming these compounds. As a general rule, more oxidized the compound is, like carboxylic acid is an oxidized compound, it will take priority. And carboxylic acid is represented by oic acid at the end. And we'll look at that when we'll come to the carboxylic acid derivatives. So at the moment, we're just talking about aldehydes and ketones. That's the one we are talking about mainly. And if a compound has got an alkene as well as an aldehyde, then the priority of the name will go with the AL at the end. So aldehyde will take priority when we naming that compound. So the arrow here indicates that these compounds at the top, they are the highest priority, and the one at the lowest, at the bottom is the lower priority. So this only applies when you have two functional groups present in the same molecule. Then you need to figure it out which one is higher priority than the other. And the name has to go with the higher priority molecule. Let's look at an example, then it becomes clearer. Maybe the example is not there. But remember that if you have more than one functionality present in your molecule, the one with the higher priority in that arrow, the name has to be according to that priority. Now, what about nomenclature of ketones? The nomenclature of ketones, we just saw that the common name for this ketone, which has one methyl group on each side, is called as acetone. And if you look at how many carbons are present in this molecule, you can see it has 3 carbons present. So it's a propanone. And on at the end indicates that the molecule has a ketone functionality. If it's 3 carbons, if propanone, if it's 4 carbon, then it'll become butanone and so on. And that applies here. If you look at this molecule here and look at the total number of carbons it has 1, 2, 3, 4, 5, 6. It has 6 carbons. So that means it's going to be a hexanone. But the question here is, how do we specify that the carbonyl is present at this position? Because if you take another example, which is also a hexanone, how would you differentiate between this molecule here? So if I put a carbonyl over here, and then I say that this is CH2, I'm going to write it 4 times. Or 3 times, sorry, if I just write that 3 times, so 3 times here, and a CH3. If you look at the number of carbons present in this molecule here is 1, 2, 2 plus 3, 5, 5 plus 1, 6. So this is also a hexanone. So how do we differentiate this hexanone from this hexanone? The difference is the carbonyl group, you have to try to give it the minimum number possible. So that's 1, 2. And if you count here, this is 1, 2, and 3. So this molecule is 3 hexanone, while this molecule will be 2 hexanone. You might ask, why don't we start numbering from that side? If we start numbering from that side, then this will be 1, 2, 3, and 4. That becomes 4 hexanone. But we try to give the carbonyl the minimum number we can give in the structure. And the minimum number can come if we start from the left or from the right. Similarly, this molecule here, that is now 7 carbons long, 1, 2, 3, 4, 5, 6, 7. So 7 is heptane, and it's a ketone, so it's an on at the end, heptanone. And the carbonyl group here, you have to try to give it the minimum number. the minimum number can only be given if you start numbering from that end, not from the other end, because if you start numbering from the other end, then the carbonyl will get a very high number. So we give carbonyl the lowest number, and then the other substituent can come after that. So now you can see that the methyl group here is present at the 6th position. So that becomes 6-methyl-2-heptanone. That's the name for that compound. If you got a cyclic structure with a carbonyl, it is automatically assumed that the carbonyl is present at the 1 position in the cyclic ring. So this becomes cyclohexanone. You don't have to say one cyclohexanone, because it is already understood that when you have only one carbonyl in a ring, then it is one carbonyl. So that you don't have to specify that. And if you got 2 ketones rather than 1, then it becomes a butane dione. And if you have 2 carbonyl present in a 5-carbon long carbon, then it's a pentane dione, because it has 2 carbonyl groups. So 2 becomes dione, mono 1 is on, and if it's 2, then it's dione. And when there's a double bond present, then you have to actually specify where the double bond is in the molecule. Carbonyl will again get the lowest number. So 3, 4, 5, and 6. So it's a 6 carbon, and it got a double bond. So that's why it's not called as hexane, it's called hexene. And 4 indicates that double bond is present at the 4th position, and 2 indicates that the carbonyl is present at the 2 position. So that's how you nomenclature, give the names to these compounds. And I'm gonna let you work it out yourself. Why, or maybe I can give you quickly a hint. Why do we call that compound 4-oxopentanal? And if you look at the table which I showed you in the priority list, the aldehyde gets the priority. So this aldehyde group is a priority group. So that is going to be 1, that is going to be 2, that is going to be 3, that is going to be 4, and that is going to be 5. So it's an aldehyde. So the name will be L, which corresponds to pentanal, 5-carbon aldehyde. And it has an oxo functionality present at the 4th position. So this ketone or carbonyl functionality is also called as an oxo group. So it's 4-oxopentanal. And the same thing here, if you think about it, the butanate part comes from the ester. So this part here is your ester, and that's high priority compared to the carbonyl. So that is 1, that is 2, that is 3, and that is 4. So this butanate, which corresponds to the ester and the oxo group at the 3 position. This is a little advanced example, so let's not worry too much about it. I just want to leave it there with you so that those of you who are really interested in it, they can think more deeply and try to understand why we are calling the names of these compounds the way we are. So this is like an advanced example, and you can spend a little bit of time yourself and then try to figure out if the names given underneath are correct. But if you can understand the simple aldehydes and simple ketones at your level, that's pretty good already, because it'll be in your 2nd year when you'll be looking at dicarbonyl compounds rather than monocarbonyl compounds. Okay, what's so special about this carbonyl group? What's so special about C double bond O? If you just look at carbon and oxygen and look at the electronegativity of the carbon and the oxygen, you will find that oxygen is more electronegative than carbon. That means it likes to pull the pair of electrons towards itself because it's more electronegative. And because of that, there is always polarization of this C double bond O that is present in the molecule. So C double bond O is going to be polarized because the oxygen is more electronegative than carbon. So that means the pair of electrons which is there between carbon and oxygen are going to be a little bit more towards oxygen, because oxygen can pull electrons better than carbon. And also, if you draw a resonance structure for the carbonyl group, we already said that the carbonyl oxygen is polarized. What if I take that pair of electrons and totally move it onto the oxygen? You will get a positive charge on carbon and you will get a negative charge on the oxygen. And this is the resonance structure for the carbonyl group. And that makes the carbonyl behave as if it got a slight positive charge on the carbon and it got a slight negative charge on the oxygen. So that means anything which is likes the positive charge, it is going to attack that carbon. And we'll see later on, the nucleophiles are compounds. So nucleophile can be represented by this nucleophile with pair of electrons, or you can have a nucleophile which has a negative charge. So they would love to attack the positive charge. So we will find that these nucleophiles, they will react with the carbonyl compounds quite readily. Another thing to remember is that this carbonyl carbon here is an sp2 carbon. It's not an alkane, it's like an alkene, it's an sp2 carbon. So that means the carbonyl group here is a planar group. Planar means in the plane of the paper or plane of the screen. So the carbonyl group is planar, and the carbonyl oxygen is slightly positive, and carbon is slightly positive, and oxygen is slightly negative. And that is responsible for the reactivity of the carbonyl group. That's why the carbonyl group can react to give you addition products. So we learned just now that the carbonyl bond is a polar bond, or carbonyl group is a polar group. We also learned that there's a partial positive charge on the carbon and there's a partial negative charge on the oxygen. So that means a nucleophile, which either has a pair of electrons or has a negative charge, it can attack that carbonyl and move that pair of electrons to oxygen. So you're gonna get an oxygen minus here, and your nucleophile adds to that carbon. Another thing to note here is that this carbon here was an sp2 carbon. It was a planar carbon, we heard. And now, after we have reacted it, you will see that this is not planar anymore. This has become tetrahedral, and this is like an sp3 carbon, okay? So the carbon atom undergoes a change from planar geometry to tetrahedral geometry, okay? And if you can find a proton H plus nearby, this is going to become an alcohol. So that means reaction of a nucleophile attacking a carbonyl could give you an alcohol product, depending upon what the nucleophile is, I must add. Okay, so let's see what's the consequence of that. So the consequence here is that the aldehydes and ketones undergo nucleophilic addition reactions with a range of nucleophile. By addition reaction, we mean that the nucleophile will attack onto the carbonyl and add to it, and it stays there in the product. So that means the nucleophile Z has added to the molecule to give you this addition product. The starting compound is a carbonyl compound, and the product is an alcohol compound. So you have converted the carbonyl to the corresponding alcohol compound. So the question is this reaction going to be reversible, or is this reaction is going to go straight to the product and you don't have to worry about it at all? That depends upon the nucleophile. If your nucleophile is a strong base, like I have represented it with the Z with a negative charge. So that's like a strong base. This reaction is irreversible because Z minus is too basic to be eliminated. So that means this reaction cannot happen. You can't bring that across and you can't kick that out. Because if you can kick that out, you will go back to your starting material. But because this nucleophile is very strong, Z minus is a strong base, it just is an irreversible reaction. It just reacts and goes to the product. But if this was a weaker nucleophile, then there's a possibility that the reverse reaction could also take place. And that's shown here. So the nucleophile Y here only got lone pair of electrons. It doesn't have a negative charge. And we'll see the examples of nucleophiles with a negative charge and nucleophiles with a positive charge. Nucleophiles with just pair of electrons in a minute. But if nucleophile just has pair of electrons, it will still attack your carbonyl group. It'll still give you that intermediate. But look at the arrows here. These arrows are reversible reaction. Because our nucleophile is not very strong, this can come back and kick the nucleophile out. And if the nucleophile is kicked out, you go back to your starting compound. So that means if the nucleophile is relatively weak, the reaction is reversible and Y can be eliminated. At the end product, if of this reversible reaction, although it is reversible reaction, it can go back to your starting compound, is still an alcohol. Okay, so nucleophile react with your carbonyl compounds to give you the corresponding addition products, and that's the nucleophilic addition. So then the question is also, are the aldehydes and the carbonyl ketone, are they equally reactive? And another thing to note in these reactions, the two reactions we saw just now, is that this group here and this group here that was present in the starting material was always present in your product, irrespective whether the nucleophile is strong nucleophile or weak nucleophile. So these groups, hydrogen, which is present in the case of aldehyde, and a carbon group, which is present in the case of ketone, these groups are not replaced by the nucleophile. So that means nucleophile cannot come in and kick the hydrogen or the R group out. It can only come in and add and give you a product. Okay, that's what I'm trying to say here. But this reaction is interesting when it comes to the acid, the esters, the carboxylic acid derivatives. In those cases, we'll see later on that this group here and this group here and the groups which are represented in red, they can actually be kicked out by the nucleophile. So these groups can be lost in the reaction. But in the case of aldehydes and ketones, you don't lose hydrogen, you don't lose carbon, you always get an addition product and that product stays. You can get a reversible reaction, but you cannot lose any of the hydrogen or the carbon that is present in it. While in the carboxylic esters or acid compounds, the derivatives, these groups can be lost, which are represented by the red color here. Okay, so in terms of reactivity then, if you just have aldehydes and ketones, which is the most reactive compound? Is it aldehyde or is it the ketone? If you write three structures here, one is the simplest aldehyde possible, that is formaldehyde, which got just hydrogen next to the carbonyl, an aldehyde which has got a carbon group, and a ketone which has two carbon groups present on the carbonyl. you will find that the formaldehyde is the most reactive carbonyl group out of these three, followed by aldehyde and followed by ketone. So generally it means that the aldehydes are more reactive than the ketones. And aldehyde is always more reactive than the ketone. Then the question you might ask is why an aldehyde is more reactive than a ketone? There must be some reason to convince. Okay, to convince you, the reason is in the case of aldehyde, so this was our starting aldehyde. The aldehyde was RC double bond O H. This was our starting aldehyde. And we reacted that with a nucleophile called Z. And Z, let's say, has a negative charge or strong nucleophile. So the product you're going to get from this reaction is where the nucleophile adds to the carbonyl group and it becomes an alcohol. So the product, this is the product from aldehyde. And the central carbon on this product here is less crowded because there's a carbon, there's a nucleophile, there's a hydroxyl, and there's a small group hydrogen. While if you start with the ketone and do the same reaction and look at the intermediate in this case, the intermediate is much more crowded than the starting compound. So you have a CO, and then you attack that with Z minus again. And this is the product you're going to get. And you will see that the central carbon on this product here is very crowded. You got a Z, you got R, you got a hydroxyl, and you got another carbon group. While the aldehyde only has a hydrogen here. So that means the product is less sterically crowded. If it's less crowded, it can form easily. So that's why the aldehyde is more reactive. In ketone, the two substituents of the carbonyl cause greater steric crowding at the tetrahydrocarbon. So because the aldehyde got a hydrogen, so there's a less steric crowding. Ketone has two carbon groups. There is more steric crowding present in this molecule. The other thing why, so one was the steric reason that why aldehyde is more reactive. So that was the steric reason. We also have electronic reason why aldehyde is more reactive than the corresponding ketone. And that is because of the electron releasing effect of the alkyl group that is present on the aldehyde. The alkyl groups, they release electrons. In the case of aldehyde, you only have one carbon releasing electron, while in the case of ketone, you have two alkyl groups releasing electrons to the carbonyl carbon. So in this case here, this carbon is going to be less positive than the carbon in the case of aldehyde, because in the case of ketone, there are two groups pushing electrons into the carbon, while here there's only one group pushing electrons to the carbonyl. So this is going to be more positive compared to this, going to be less positive. If it's more positive, then it's more reactive. And if it's less positive, then it'll be less reactive with the nucleophiles. So comparing aldehyde and ketone, the aldehyde group is more reactive than ketone. So now let us look at some real reactions of the carbonyl compounds with the nucleophiles. And the first nucleophile we're going to look at is the Grignard reagent. And I'm going to show you what a Grignard reagent is in a minute. But I can tell you that the person who discovered this reagent, Grignard, got a Nobel Prize for it, for this discovery. And the Grignard reagents are examples of nucleophiles, carbon nucleophiles, which are highly reactive and strongly basic. And Grignard reagent is typically represented by R, M, G for magnesium, X for a halide. So that can be R, magnesium, chloride or bromide or iodide, it doesn't matter. So this is like a Grignard reagent. Magnesium chloride, alkyl magnesium chloride, aryl magnesium chloride. You can have any carbon group here as a magnesium salt. And these reagents are called as Grignard reagents. And we'll see in a minute, in this Grignard reagent, R behaves like a nucleophile, R minus, and then the positive charge is on magnesium. So that means the R minus acts as a nucleophile. And the Grignard reagents, they react with all carbonyl compounds, aldehydes, ketones, carboxylic acid, and derivatives. They can react with all. And the addition of the Grignard reagent to the carbonyl compounds is used to prepare alcohols. I told you earlier, when the nucleophile reacts with carbonyl, you get an alcohol. You can prepare primary alcohol, you can prepare secondary alcohol, and you can prepare tertiary alcohol if you like. You can even prepare carboxylic acid by the reaction of Grignard reagent. A primary alcohol is when you just have a CH2OH present in a molecule. That's an, sorry, I just draw it again. It's R CH2OH. That's an example of a primary alcohol. CH2OH is a primary alcohol. And similarly, you secondary alcohol, tertiary alcohol. I'll show you in a minute what they look like. And the result of the Grignard reaction with the carbonyl compound is that you form a carbon-carbon bond. And carbon-carbon bond formation is very important in organic chemistry because you want to link two carbons together to form longer molecules. This reaction is absolutely essential in organic chemistry. And Grignard reagent, as I mentioned, is represented by organic magnesium halide. This halide can be a chloride, can be a bromide, can be an iodide. And it was discovered by a French chemist, Victor Grignard, in 1900. That's 120 years ago almost. And he received a Nobel Prize for this discovery. Then the question you might ask is that, how do we prepare these Grignard reagents? And I told you already, in Grignard reagents, R minus is your nucleophile. Making the Grignard reagents is very easy. All you need to do is to take an alkyl halide. Again, X here can be chloride, bromide, iodide, and then heat it with magnesium metal. You can find magnesium turning, you can get magnesium powder, and you heat it together in a solvent like ether, a solvent which is dry and solvent which does not have any water, because the Grignard reagent is very reactive and it can react with water if we are not careful. So you just heat them together. It's a very exothermic reaction and you get the corresponding Grignard reagent formed in that reaction quite readily. The oxygenated solvents are really good solvents for this Grignard reaction because the oxygen can complex with the Grignard reagent to stabilize it further. So that's why typically Grignard reagents are made in oxygenated solvents like ether or THF or something like that. So here's an example. You take an ethyl bromide, you react it with magnesium, and you form ethyl magnesium bromide. And the good thing about this is that that carbon here is going to act like a nucleophile like that. Similarly, you take bromobenzene, magnesium ether. This is going to behave as if this compound is, you have a benzene ring and you have your minus group here and MgBr. So this is going to be your nucleophile that can react with carbonyl compounds. I was telling you it's a very polarized molecule. The carbon is minus, magnesium is positive. The other way of looking at it is if you look at electronegativity of carbon and you look at electronegativity of magnesium, you will find that carbon is much more electronegative than magnesium. So that means the negative charge sits on the carbon and not on the magnesium. So this is your nucleophile in that Grignard reagent. The structure of Grignard reagent is not as simple as that, but I don't want to go into too much detail here at your level. All you need to understand is that the oxygen that is present in ether or oxygenated solvents, they can complex with the magnesium, and that stabilizes this highly reactive Grignard reagent. And it can be represented with a negative charge on carbon and the positive charge on magnesium. So your nucleophile in the Grignard reagent is the carbon nucleophile, and that can react with the carbonyl groups. Grignard reagents are very sensitive to water. So you have to make sure that when you're making these Grignard reagent, there cannot be any water present, because if there's water present, the Grignard reagent will react with water to give you the corresponding alkane compound. If you start with CH3, CH2Br, it'll become CH3, CH3, and your Grignard reagent is destroyed. And if the Grignard reagent is destroyed, it wouldn't work. So you can't have alcohol or water present in your reaction. You can only use ether, and even ether is typically dried to make sure there's no water remaining in it. If there's no water remaining, only then you use it, because otherwise the Grignard reagent doesn't work. Okay, now let's look at some reactions to see what products you will get. If you take a Grignard reagent represented by RMGX and react that with formaldehyde, that's our simplest possible aldehyde, the R minus will attack your carbon positive, moving that pair of electrons over there, and that becomes like a magnesium salt. And typically after the Grignard reaction, you add some aqueous acid into your reaction. When you add aqueous acid, this intermediate will convert to the corresponding alcohol. And this alcohol is a primary alcohol because the carbon here has two hydrogens. When a carbon has two hydrogens present on it, it's a primary alcohol, like CH2OH is an example of a primary alcohol. So if you have, say, CH3, CH2OH, and if I put CH3 here, this is ethanol, 2-carbon alcohol. This alcohol is primary alcohol. There you go. And this is a real example. If you take methyl magnesium bromide, you will get ethanol compound as the primary alcohol. What if this was an aldehyde compound with a carbon group attached to it? So now it's not a formaldehyde, but there's a carbon group attached. The reaction will work the same way. R minus attacks that carbonyl, forms this magnesium salt, and when you add aqueous acid, it becomes an alcohol. And this is an example of what we call a secondary alcohol. A secondary alcohol is when you got only CHOH present in your molecule. So if you have CHOH present in your molecule, that is called as a secondary alcohol. And you're going to have 2 carbon substituent present, obviously, on that C. So this is like a secondary alcohol. And that's a real example, methyl magnesium bromide reacting with acetaldehyde to give you this 3-carbon alcohol, which is 2-propanol. That's the 3-carbon alcohol compound in that reaction, give you a secondary alcohol. What about reacting it with a ketone? Instead of aldehyde, if you react it with a ketone, which already has 2 carbon groups attached to the central carbon, the R minus here will attack your carbonyl to give you that intermediate magnesium salt, and then aqueous acid workup will give you Now, a tertiary alcohol is when there's no hydrogen present on that carbon, only an alcohol group and a carbon group, carbon group, carbon group. So no hydrogen present on the carbon that has the OH group. So this is called as a tertiary alcohol. And that's a real example here. Same methyl magnesium halide reacting with this ketone, which has CH3CO, CH2, CH3. Same reaction, exactly the same way. Form the magnesium salt, add water with a bit of acid, you will get the corresponding tertiary alcohol in very high yields. So you can make primary alcohol, secondary alcohol, tertiary alcohol. Start with formaldehyde, you get primary alcohol. Start with aldehyde, you get a secondary alcohol. Start with a ketone, you get a tertiary alcohol. So that's the beauty of this reaction, that how powerful it is. And in each reaction, you form a carbon-carbon bond. So it allows you to form a carbon-carbon bond. The Grignard reagent can even react with carbon dioxide. So this C double bond O is carbon dioxide, can be written as CO2, carbon dioxide. So Grignard reagent can also react with carbon dioxide. The carbon minus here can attack the carbonyl, moving that pair of electrons over here to give you a magnesium salt. And when you add water, you get the corresponding acid compound. So what I have shown you is that the carbonyl group is a reactive group. It is a polarized group where carbon is slightly positive, oxygen is negative. So the nucleophile, which is negative, in this case, the Grignard reagent, where the nucleophile is carbon is negative, it can attack the carbonyl to give you the alcohol, primary alcohol, secondary alcohol, tertiary alcohol, and even carboxylic acid. And now, actually, I'm going to ask a few questions to you. What I want you to do is think about what would be the product of this reaction. You have this ketone compound, you have this ketone compound, you have this aldehyde compound, and you have this Grignard reagent, Grignard reagent, Grignard reagent. What would be the product of this reaction? I want you to think about it for a few minutes, and then I'm gonna give you the answers. But let's have a break for 5 minutes, and then think what would be the product of this reaction. So I want you to think what would be the product of this reaction, and I'm gonna give you 5 minutes to do it. I'm gonna mute my.
All right. Okay, Prof. Naresh, you're still mute. Okay. Okay. So, dear all of the students, you can think what the answer, what the alcohol, the product from these reactions. So, for about 5 minutes, so Prof. Naresh Kumar can be takes time. Okay. Maybe you can draw the mechanism in your books, so you can know what the alcohol that is it the primary alcohol or secondary or tertiary or even or carboxylic acid. Yeah, so you can. And if you have any questions about the Grignard reaction, you can ask. You can raise hand or discuss with the Prof. Naresh.
Or maybe Bu Amel, the student can ask in Bahasa Indonesia and you can translate. Yeah.
Okay. If you have a difficult about the English, you can ask with the Bahasa, and I'll try to deliver with to the Prof. Naresh.
Mm-hmm.
Yeah. Jangan takut ya. Tanya saja nggak apa-apa, mumpung ada Prof Naresh di sini. Ya.
Okay, I'm back. I hope you all got the answer. The way to answer this question is that in this Grignard reagent, think about where will be the negative charge, because Grignard reagent carbon is negative. So that CH2 here is a negative part of the molecule. And this will attack your carbonyl group over here. Because carbon is positive, you can say this my carbon is positive, slightly positive. And this part is slightly negative. So that means CH2 will attack there, and this will move over here, and that becomes your alcohol. So that means the carbon here with a double bond oxygen is going to become an alcohol. And your CH2, CH3 is going to come at the bottom. And the other groups are not affected. They're just going to sit there, because we learned that in aldehydes and ketones, you can't lose any of the carbon or the hydrogen from your molecule starting compound. So it's going to be CH3 over here, and it's going to be phenyl ring over here. So this is the product you're going to get from this reaction. Easy, right? And in this Grignard reagent, this is minus, and you can attack, you can attack that either from the top or the bottom, it doesn't matter. That carbon over there, and this is going to move over here. So that means what that is going to become in your product is going to be a 5-membered ring that is not going to be affected. And you're going to get an OH group forming there. And then you're going to have your CH3 attached over there. So that's going to be your alcohol product being formed. And you should think whether this is a tertiary alcohol or is it a secondary alcohol. Similarly with aldehyde, you're going to get the same thing happening, that coming here, attacking your carbonyl, moving that pair of electrons at the top to give you the alcohol. So all you need to do is to worry about the carbonyl group, nothing else. Put the hydroxyl here, and then you put your CH3 underneath it. And then you have your hydrogen here and phenyl over here. And you can then think for yourself whether this is a secondary alcohol or these are tertiary alcohols. So that's easy for you to work it out. So very easy to work out the products for these reactions. If you just remember which part of the molecule is negative and which part of the molecule is positive, you can figure it out very easy. And you can also look at the central carbon. If it got no hydrogen on it, this is a tertiary alcohol. And similarly, this carbon here has no hydrogen. There's a carbon group here, carbon group here, carbon group here, and OH. That's also a tertiary alcohol. And this one has got one hydrogen, not two. If it got one hydrogen, then it's an example of a secondary alcohol. So this product is a secondary alcohol. Okay, let's get moving. Next one. You can also, instead of using a Grignard reagent, you can also what we call organolithium reagents. Organolithium reagents are like CH3 lithium, phenyl lithium. Again, carbon is more electronegative than lithium. So CH3's lithium behaves exactly the same way as CH3 MgBr. So if you have CH3 MgX or chloro or bromoid, iodo, doesn't matter. This also have minus. The lithium compound also does the reaction exactly the same way to give you the alcohol compound. So you can use, sometimes it is advantageous to use lithium compounds than the Grignard compound, depending upon how easy it is to make. Okay, you can even stretch this reaction further. you can take a triple bond, carbon-carbon triple bond, and a acetylene compound with a negative charge. And that also behaves like a nucleophile, a carbon nucleophile. And that can be derived from acetylene. This is an acetylene compound. The hydrogen which is present on the acetylene compound can be removed because you got a triple bond, carbon-carbon bond present, and there's a hydrogen here. This hydrogen here can be removed by using a strong base. This is like an acid-base reaction. This is your base, sodium amide. So say sodium amide is minus here, and sodium is positive. This is like sodium hydroxide is NaOH, is your sodium hydroxide. Sodium amide is a very strong base. It's stronger than sodium hydroxide. So that base can take away that hydrogen which is present on acetylene. And if it takes away that hydrogen from acetylene, you can form a salt of the acetylene. And this nucleophile here behaves exactly the same way as a Grignard reagent. It's like the Grignard reagent had a negative charge. This salt also has a negative charge. So that means the negative charge will attack the carbonyl in exactly the same manner. And if it attacks it exactly the same manner, you can add that group onto your carbonyl compound to get an alcohol. So that means the carbonyl group can react with Grignard reagents, can react with organolithium reagents, can even react with acetylide ions. That means carbon, triple bond carbon with a negative charge. So you can see how useful this reaction is, that you can do this reaction with many different nucleophiles, carbon nucleophiles we're talking about for the time being. Now, what about other nucleophiles? So the addition of carbonyl that we have looked so far involved a carbon-based nucleophile. So all the reactions we've done so far had carbon as a nucleophile with a C minus. Whether it was a CH2, it doesn't matter. Whether it was a C triple bond C, didn't matter. As long as it has that negative charge, the reaction with the carbonyl took place quite happily. But carbonyl compounds can also react with a range of other nucleophiles as well. And some are charged and some are neutral species as well. And we'll see examples of that now in the coming slides. What about a cyanide? If we take a Cn minus, can it react with the carbonyl? What about Cl minus? Can we have a Cl minus reacting with a aldehyde? Can we have Br minus? Can we have iodide minus? Can they react with an aldehyde compounds? And these are obviously not as strong nucleophiles as a carbon nucleophile. But cyanide, Cn minus, is also a nucleophile. And this reaction involves the reaction of a carbonyl group with HCN. Okay, HCN is a hydrocyanic acid. It's a very poisonous acid. You can imagine that cyanide is a very toxic chemical. And this reaction, what we are trying to see is, can a Cn minus react with a carbonyl compound? So this is what we are interested in, finding out, can a Cn minus attack that carbonyl to give us an alcohol where you have a cyano group present in the molecule and an alcohol present in the molecule as well. And this reaction is typically carried out by using cyanide as a catalyst. So this can be a sodium cyanide. This can be a potassium cyanide. It doesn't need a small amount of sodium or potassium cyanide as a catalyst, where Cn minus is the catalyst. It is obviously the addition of HCN to this molecule. You can see cyanide is there, hydrogen is there, HCN is added to the molecule. but it requires a small amount of cyanide as a catalyst. And I'll show you why it requires cyanide as a catalyst. In the first step, the cyanide attacks the carbonyl here to give us the intermediate compound, exactly the same manner as we saw in the case of the carbon nucleophiles. Attacks, gives you O- as a magnesium salt. So this kind of compounds where you have a hydroxyl as well as cyanide present on the same carbon is called as a cyanohydrin. So the nucleophilic addition of cyanide to the carbonyl gives us a cyanohydrin compound. The first step is attack of cyanide onto the carbonyl. This is a reversible reaction. You get the formation of this intermediate oxygen minus because the cyanide is not as strong nucleophile as a Grignard reagent. It's a weaker nucleophile. That's why this reaction is reversible. You may recall in the beginning when we talked about Z minus and Y as two nucleophiles, if it was a strong nucleophile, the reaction was not reversible. But if it's a weak nucleophile, the reaction is reversible. So this intermediate that is formed reacts with HCN to form the cyanohydrin, and the cyanide is regenerated in the reaction. That's why the catalyst in this reaction is the cyanide catalyst. Sodium cyanide or potassium cyanide is your catalyst because it is regenerated at the end. We did not use the cyanide in the reaction. It just helped us to do the reaction. That's a typical definition of a catalyst. The catalyst is not consumed in the reaction. It is regenerated after the reaction. So this is what happened here. The catalyst is regenerated. Okay. So the cyanide can react. You might ask that if we add a cyanide to a compound, does it become toxic? Because we know that potassium cyanide, hydrocyanic acid is very, very toxic, is poisonous. Can cyanohydrin be toxic as well? The answer is no. If you look at this compound here, it's called linamarin. This has got a cyanide group present in it, as well as an oxygen functionality present on the same carbon. So it has got a cyanohydrin group present in this molecule. And this molecule actually is found in cassava roots. And cassava cakes are very yummy. I don't know if you have tried cassava cakes. I think cassava cakes are very popular in Southeast Asia.
Yes.
And these cakes come from cassava. And cassava root has this cyanohydrin compound. But maybe the cyanohydrin is destroyed during cooking. So there is no poisonous effects associated with this cassava compound, which is found in cassava roots. So the cyanohydrin can be naturally occurring compounds as well. So it's not that only can be made synthetically, they also occur naturally. The same reaction, if you try with HCl or HBr or HI, you will find that there'll be no reaction at all with those acids. It's just that the reaction of the cyanide, HCl, HBr is a reversible reaction. And because it is a reversible reaction, the equilibrium does not lie toward the product, it lies towards the reactant. So HCl, HBr, HI cannot add to the carbonyl, but cyanide does. Okay. Can we have another different nucleophile which is also negatively charged? And what I'm going to talk about now is reaction of carbonyl compounds with hydride ion. By hydride ion, we mean H minus is a hydride ion. We talked about carbon nucleophiles when we are talking about Grignard reactions. Now we're going to be talking about H minus as a nucleophile? Can it attack the carbonyl group? But before we attack the carbonyl group, you're going to ask, where does this hydride come from? So H minus is called as hydride. Where does this hydride come from? The hydride can come from two reagents. One is called as sodium borohydride. NaBH4 is a white powder and it's a mild reagent. And the second one is called as lithium aluminium hydride, and it's a more powerful agent. And we're going to see that the hydride actually adds like a hydrogen to the molecule, to the carbonyl. And if you add hydrogen to a molecule, it's a reduction reaction. So that's why many times the reaction of hydride with a carbonyl is called as a reduction reaction, and we'll see that in a minute. So treatment of an aldehyde or a ketone with a hydride followed by protonation. Protonation is important. Protonation was also important in Grignard reaction. You added hydrogen to make the OH alcohol compound, the primary or the secondary alcohol. So let's see some real examples. How does it work? First of all, like I said, both these reagents here, which are our hydride reagents, hydride acting as a nucleophile, they will react with the carbonyl compound. So in the first instance, the H minus will attack the carbonyl compound, giving you this intermediate O minus species. And then the protonation, you need H plus to form the alcohol. And this H source of H plus can be even the solvent methanol. So this group here is what we call methanol, and methanol, ethanol are examples of solvents which are used in chemistry. Sorry, I couldn't draw there properly. CH3OH is called as methanol, and the OH group is there. This O minus here is a very strong base. It can remove this H from methanol or ethanol to give you the corresponding alcohol molecule, and O minus, OMe minus is released from the reaction. So that means if you do your reaction in methanol or ethanol or even aqueous solvent, aqueous means even water as a solvent, with borohydride, because it's a mild reagent, you don't even need to add acid at the end of the reaction. Remember when we were doing the Grignard reactions, we were reacting it with the Grignard reagent, and then we were adding aqueous acid at the end. But here, when you're doing the hydride reaction, you don't even need to add acid in the case of borohydride, because the solvent, which is typically an alcohol solvent or water solvent in these reactions, the proton, the H plus, can come from that to give you the corresponding alcohol compound. Now, if you look at the structure of this group here, this is the CO group, and the product is an alcohol. So we added a hydrogen over here, and we added another hydrogen over here. So what we have done is we have converted the C double bond O into CHOH. So that means we added two hydrogens across that carbon-oxygen double bond. An addition of hydrogen to a molecule is called as reduction. So that means you have done the reduction of the carbonyl group to the corresponding alcohol compound. On the other hand, if you take lithium aluminium hydride, which is a very strong reactive reagent, you cannot use alcohol as a solvent for lithium aluminium hydride. Most of you would not have worked with lithium aluminium hydride before. Lithium aluminium hydride is a gray powder. If you take some lithium aluminium hydride and sprinkle it over water, it flashes of light or flashes of fire will come out because it reacts so rapidly with water that it can catch a fire. It can start a fire if you're not careful with this reagent here. It's very, very reactive reagents. It can react with water. It can react with alcohol. So the solvent we use for this reaction when we use lithium aluminium hydride is an ether solvent which does not have any water. Okay. So in that case, if you're using ether, the proton cannot come from ether because ether has got no polar OH group. So this is the example of diethyl ether. So if I just take diethyl ether is CH2, CH3, and on this side it also has CH2. Sorry, excuse me, the drawing is a bit hard to do. CH2, CH3. So this is your diethyl ether. And diethyl ether has not got a proton which it can give away compared to methanol or ethanol. So if in case of methanol or ethanol, as you saw in the last slide, you were able to remove that proton which was present in the OH group. But here you don't have that. So that means you have to add extra acid at the end of the reaction to isolate your alcohol compound. So the message here is that the hydride can also react with your carbonyl compound, do nucleophilic addition, and also the result is alcohol. If you use an aldehyde as a starting material, you will get a primary alcohol in that reaction. If you use a ketone, you will get a secondary alcohol in that reaction. Just to give you real examples here, if you take an aldehyde, a butanal 4-carbon aldehyde, and you use borohydride as a reagent, so again, don't worry about the structure of borohydride. Just remember that this is a source of H-, and H- will attack your carbonyl. Put that over there, and that will become an alcohol. So that means you will simply get an OH over here. That's from your alcohol, right? And the hydrogen is always present here. And the other hydrogen goes over there. And that becomes your alcohol, which is same as that, butanol. Okay. And if you start with the ketone C double bond O, you will get, there's a hydrogen present here as well. You will get the corresponding secondary alcohol. This is primary alcohol. It has CH2OH. And the bottom one has only one CH. So that is your secondary alcohol. So the ketone will give you a secondary alcohol. Aldehyde will give you a primary alcohol. Again, questions for you. I have questions for you again. I want you to work out what the product of this reaction going to be.
Yeah.
It's given you a hint already what alcohol is formed when each compound is treated with borohydride in ethanol. Borohydride is a mild reducing agent. It can reduce aldehydes, it can reduce ketones, but it cannot reduce amides and esters and so on. But aldehydes and ketones can be quite easily reduced by alcohol.
Okay.
Yeah.
If anybody has questions so far, I can answer the questions now if you like. And you can try this for a couple of minutes and then we can look at the answers as well.
Okay, Prof. Naresh. Maybe there is one question from the participant. Maybe while we waiting for the examples question, we can answer the
question. Okay.
Yeah. Okay. So, there is
right.
a question from Kabir Abu Bakar.
Yep.
If the nucleophilic cyanide ion attacks the electrophilic carbonyl center, maybe why the product from Racemic? Maybe the slide.
Yep, that's a very good question. I didn't address that.
cyanide.
I'll go back to it now. And okay, let's go back to it and then we can talk about it. This one.
About the Racemic product.
Why do we get a racemic product?
Yes.
You may recall that in the beginning I said that this carbon here is an sp2 carbon and carbonyl group is a planar structure. So I said in the beginning that when you had carbonyl compound is a planar compound. By planar compound, I mean it's just like two-dimensional compound. You can imagine my hand like that. That's a planar structure. It's plane, right? So this, just imagine that the carbon is here and oxygen is on my fingers, carbonyl. So when the cyanide comes, cyanide can come from the top, attacking that carbonyl, or the cyanide can come from the bottom, attacking that carbonyl. So there's two ways the cyanide can come, from the top or from the bottom. And if you look at this molecule here, the central carbon has got 4 different substituents attached to it. You got a phenyl, you got a OH, you got a cyanide, you got a hydrogen. Whenever there are 4 different substituents attached to a carbon, this carbon here is called as a chiral carbon. That means that there is a mirror image compound possible. If I put a mirror in the middle here, this molecule, and draw the structure on this side, you will get a mirror image structure. So I can put an OH group here, and the mirror image structure will be where the cyanide will be on this side. And you will have your phenyl. Sorry, I'm drawing it the wrong way. So this will be cyanide over here. Your mirror image will be N and C over here. And your hydrogen will be over here. And your phenyl group will be over here. So there is a mirror image possible. And these 2 compounds, they are different. They are not the same. They are mirror image of each other. Just like my left hand and right hand, I cannot put my left and right hand together because the thumb is pointing this way, the other thumb is pointing this way. So they are like non-superimposable mirror images. Like left hand is a mirror image of right hand, but I cannot superimpose them. I cannot superimpose them like that. The thumb is pointing this way and thumb is pointing the other way. So whenever you have 4 different groups present in a molecule, there is a mirror image possible. When these 2 are present in 50-50 proportion, then the mixture is called as a racemic mixture. So there's 50% of that, and there's a 50% of that, and that becomes a racemic mixture. The reason it is a racemic mixture because cyanide can come from the top, cyanide can come from the bottom. And there's equal probability. There's no differentiation from the top and the bottom. And that's why we call that molecule a racemic molecule. That means it does not have any chirality. I hope you have done chirality mirror image before. If you haven't, I can go in a bit more detail, but there are mirror image possible. And just like L-glucose and D-glucose, if you take L-glucose and D-glucose, one glucose is sweeter and the other glucose is bitter, because they're mirror image of each other. And in drugs, this is very, very important in pharmaceutical drugs. If the compound has 50-50 mixture, one component is active drug, the other component might be toxic.
Yes.
And there was an example in Australia. There was a drug which was developed in Australia. It was called thalidomide. And that drug was used to treat morning sickness in women when they were pregnant, and the morning sickness, that drug was used to treat morning sickness. And that was a racemic mixture. It wasn't realized at that time that 50% of the molecule was drug and 50% of the molecule was bad. And the bad caused birth defects in children. So there was a big court case later on that the drug shouldn't have been marketed because it was a racemic mixture. So chirality is very, very important in pharmaceutical compounds. But in this reaction, because you got a planar structure, you can get cyanide coming from the top, cyanide coming from the bottom, you get a 50-50 mixture. And we call that a racemic mixture. That's why there was a racemic there. I hope that answers your question.
Okay, thank you, Prof. Naresh.
Okay.
I think Kabiru already, or maybe you have any question, Kabiru? Is it enough? Answer your question, I think. Yeah. Okay.
Yep.
Okay.
All right.
Thank you, Prof. Naresh.
Sorry, I didn't see the
Very
question in
clear.
the chat earlier, so that's why I continued.
Okay.
Okay.
We back to the
Back to the answering these
sodium
questions.
borohydride question. Okay.
Yeah. I hope you got the answers already, but I can give you the answers very quickly. The main thing you need to think about is that this is your H minus here, and the H minus can attack your carbonyl and the oxygen will go up. So basically you will get an alcohol molecule, which is easy. So you will get just an OH here. Sometimes people don't write hydrogen when they're present on carbons, but I can write a hydrogen for you just to make, just to make it easier for you, that this is the alcohol that is formed. And similarly here, if you have a hydride, H minus, and then that also will attack your carbonyl over here. Sorry, excuse, my mouse is not very good. And that will go to the alcohol. So again, you will get the corresponding compound with an OH and a hydrogen and your other group over here. That doesn't matter what that group is, you will get the corresponding alcohol. Now this one is a little tricky. You have two carbonyl groups, one carbonyl over here and one carbonyl over here. And then you want to ask yourself, is both of them going to react or only one going to react? So you should look at this group here. This is the aldehyde group. And this group CONH or CO nitrogen group is called as an amide group. So this group on the left is an amide group. And amide group is not reduced by borohydride because borohydride is a weak reducing agent. It can only react with aldehyde. So that means the amide part of the molecule is not going to be able to react. So this group here is not going to be affected. So this group is going to stay intact. And the nitrogen is sitting there. That's not reacting. Oops, sorry. This one is going to form the corresponding, my screen is playing up. Let me just draw that. Come on. Oops, sorry. For some reason. Okay, I try to draw it here because I won't draw the whole structure. I'll just say nitrogen over here. And then the aldehyde is going to become OH. And hydrogen is intact over there. And then there's a hydrogen over here. So this is the product you're going to get from this reaction, where this side of the molecule is not touched. So that stays the same. Double bond, double bond oxygen stays over there. And this is your, the 6-membered ring is not affected. So that's the product. The amide wouldn't react, only the aldehyde react in this question. Okay, how are we going with time? We still got a few more minutes.
Yeah.
I'm just going to introduce one reaction to you, and we're going to discuss this reaction in the next lecture. But this reaction is a very, very important reaction. This is a reaction where the amine is your nucleophile. So the nitrogen here has not got a negative charge, but it got a pair of electrons. And that nitrogen is your nucleophile. And in this case, when an aldehyde or a ketone reacts with a primary amine. We're going to talk about a primary amine first, and NH2, you get the formation of a C double bond N. The C double bond O is replaced by NH2. It almost gives the impression that if I have my NH2 here, and many times the students make mistake that when we ask them the reaction between a carbonyl and an amine, they just say, oh, it's just a reaction like that. And I remove this water molecule from here, and I get this product, C double bond N. The product is all right, but it's not a simple removal of water from the aldehyde to the amine. There are two steps involved in this reaction. And it's going to be addition of amine followed by dehydration, not just one step. So most students, the mistake they make is they say, oh, I'm going to react with a carbonyl with an amine, I'm going to remove water, and I get this product. The product is correct. It's called imine, but it's not a simple removal of water from this reaction. And it's going to be, I'm going to show you the details of that reaction, how it works a bit later. But imines are very, very important compounds in many metabolic pathways. If you look at the biology, living systems, you will find that imine reaction is a very important reaction. And I'm going to leave this reaction with you, which is reaction of a primary amine with an aldehyde, which is involved in vision. Like the reason we can see things with our eyes is this reaction, which is shown in this slide. And this reaction make us see what we see in the world outside. And that's the formation of an imine. And aldehyde, which is present in this molecule here called retinal, which is present in our eyes, reacts with a protein which has an amine group. The protein is called as an opsin. So you got retinal, and it's a cis retinal because it's a cis double bond here, and you would have learned about cis and trans, or you'll be learning about cis and trans when we do alkenes. The two groups are on the same side, that's cis, and opsin is a protein that is present in the eye as well, and we're not going to worry about what the structure of the protein is, but the protein has an amine group. And the retinal also have this aldehyde group, which is C double bond H. And what happens in the vision process is that the opsin reacts with retinal. The aldehyde reacts with amine to form an imine. C double bond N is formed. And this is called as rhodopsin. So when the light from outside hits this molecule in our eye, this cis bond here turns into a trans double bond. The cis double bond here becomes like a trans double bond. And this cis-trans conversion creates a nerve impulse. And this nerve impulse goes into our brain. And our brain can then convert that into vision. So this is the chemistry of vision. This is how we see things, is dependent upon a reaction between a carbonyl compound and an amine to give you an imine. And this light here, when it goes into the eye, it converts rhodopsin, cis double bond into trans double bond, which in turn generates this nerve impulse. And this trans can go back to cis, and this vision process continues. Okay, so this is the chemistry of vision, a reaction of a carbonyl with an amine compound. Reaction of an amine with the aldehyde or a ketone is not a simple dehydration reaction. There are two reactions involved. One is what we call an addition reaction. That's the nucleophilic addition reaction we've been learning all along today with Grignard reagent, with hydride adding onto the carbonyl, giving you the addition product. In this case, the nucleophile is an amine. And the amine has a pair of electrons. So nitrogen is negative again, but there's no negative charge. It's just a pair of electrons. And nitrogen attacks that carbonyl, in the same way, you get this intermediate O- compound. And this nitrogen becomes positive because it has got 4 groups attached onto it. There's 2 hydrogen, there's R, and there's a carbon-nitrogen bond. That's the new bond that is formed. So what happens is a proton transfer happens. This got an excess proton. NH2 plus is an excess proton. It can give away one of its proton to the O- to become NHOH. And this molecule is called as an amino alcohol because there's an amine and there's an OH. It becomes an amino alcohol. And also look at the arrows. This is a reversible reaction. It's not a straight reaction. It's a reversible reaction. It's not an irreversible reaction. So the first step in the formation of imine is the addition reaction. And the second part of the molecule is elimination of the water molecule. And typically in this reaction, acid acts as a catalyst. A small amount of acid, if present in the reaction, it makes it go forward. And this OH here gets protonated by the acid, becomes OH plus. And then you get a dehydration reaction happening. You get a water removal from this reaction to give you this C double bond N compound. So the formation of the imine, reaction of an aldehyde or a ketone with a primary amine, is an addition followed by dehydration. So there are 2 steps involved. One is addition and the second is dehydration. And this is a pH dependent nucleophilic addition elimination. So removal of water is elimination. So you get nucleophilic addition and then you get elimination of water. And typically this reaction works best when the pH is between 4 to 5, and 4 to 5 is an acidic pH. So that means it allows the protonation of the OH and the protonation then loses as water, and the H plus is regenerated. So it's like a catalyst. It's not used up in the reaction. Okay, I think I will stop here for today, and then I'm happy to answer any questions you might have. I think we probably come to the end of the time, but we'll continue with this carbonyl reactions in the next lecture as well. So if you have any questions, you can ask me now if you like.
Okay, thank you, Prof. Naresh, for the clear explanation about the some of reaction in carbonyl, especially. Okay, dear participant, all of the students, if you have any questions, please raise your hand so you can discuss with Prof. Naresh, or you can chat in the chat box. You can use a bahasa, and I will try to deliver to the Prof. Naresh. Okay. Okay. Maybe while we wait the student, I want to ask to Prof. Naresh. Is it okay, Prof? All right. About the carbon as a nucleophile, Prof. So you later you said that the carbon can be a nucleophile from the Grignard or lithium or from cyanide, but the reaction may be the reversible and also irreversible, right? How we can maybe some students can confuse how we can know when the carbon as a nucleophile nucleophile how to say irreversible mechanism, and or when the C nucleophile can irreversible.
Okay, let's specific. Okay, let me just find a little blank space if I can find somewhere and try to explain that a little better. Maybe I can go maybe here and try to explain it here. In order to work out whether the nucleophile is a strong nucleophile or a weak nucleophile, you look at what is the conjugate acid for that compound is. So if I say, look, we talked about Grignard reagent. We had HCH3 MgBr, right?
Yeah.
This is our Grignard reagent. And we said that this is a strong base. So this is CH3 minus, right? And it will have a conjugate acid. Every base has a conjugate acid. The conjugate acid for this compound will be CH4. Okay?
Yeah.
And then we had CN minus, and we said this is our cyanide nucleophile. And the conjugate acid for that cyanide will be HCN, right?
Yeah.
So CN minus comes from HCN, and CH3 minus comes from CH4. This is like the conjugate acid. So you can look at whether the conjugate acid is a strong acid or a weak acid. If the conjugate acid is a very, very weak acid, this is going to be very, very strong base. So this is like a weak or the weakest acid you can find. This is very, very weak acid, or hardly any acid. Is very, very weak. But CH3 minus is conjugate base. It's going to be very, very strong. The cyanide here, and if you look at HCN, HCN is a stronger, relatively stronger acid. It's still a weak acid, but not as strong as HCl or HBr. But it is still stronger acid than CH4. Because in CH4, you cannot remove easily a proton because it's a very, very weak acid. While here you can remove still a proton because it's a stronger acid. So in order to work out which is the stronger nucleophile or a stronger base, you look at the conjugate acid. And if the conjugate acid is very weak, then the corresponding base is going to be very, very strong.
Yeah. Okay,
that's how it works.
Yeah, thank you, Prof. Naresh. So basically, acid-base conjugate. Yeah.
Exactly.
Okay. Thank you very much for the explanation.
Okay.
All right, students, ya, adik-adik mahasiswa, ada pertanyaan? Silakan. Silakan bertanya, nanti bisa saya sampaikan ke Prof. Naresh.
Actually, Bu Amel.
Oh ya, Bu Vidya.
Actually, Bu Amel, I have one question for Professor Naresh.
Okay, please, Bu Vidya.
All right. Hi, Professor Naresh.
Hi.
Yeah, I'm sorry, I'm on my way. I would like to ask about the mechanism reactions of the nucleophilic addition of the carbonyl compounds. So, is it necessary for the oxygen atom of the carbonyl group? Should it be protonated first before attacked by the nucleophile?
No, I mean, when you got a strong nucleophile like Grignard reagent, you don't need to protonate, because if you have acid present in the presence of Grignard reagent, the Grignard reagent will be destroyed. But when you're reacting it with amines and the like, you can have the acid acting as a catalyst in those reactions. So for example, in the amine reaction, if you protonate this carbonyl, then you can say this reaction can be faster because you can get the alcohol directly. So in case of stronger nucleophiles, you don't need to worry about protonating the carbonyl to have a higher reactivity. But in the case of aldehydes and ketones, the proton can help. The pH of the reaction can help in terms of dehydration, but it also could help you with the protonation of the carbonyl, which will then increase the reactivity as well. So I think Vidya's question, if some people didn't understand, was that can you form from the acid, say if you have a carbonyl compound, can you form C double bond O? I think we talked about this in the second year lectures where we were looking at ketoenol chemistry, that can we protonate this first? So if there's an acid, can we put a proton here? And that puts a positive charge on the oxygen. And that makes this carbonyl even more reactive, because then the nucleophile say with the lone pair of electrons, can come and attack that carbon, and then that compound becomes directly the OH compound. It becomes directly the OH compound. You don't have to go via this O minus. Yeah, that is possible. So when you got a weaker nucleophile, you can get protonation of the carbonyl and then attack of nucleophile. That's a possibility.
Okay, so it depends on the nucleophile itself.
Yes, that's right. So weaker nucleophile will be assisted by the presence of acid.
Okay.
While
Thank you.
the strong nucleophile, it doesn't matter. The acid, you don't need that because acid will destroy the Grignard reagent if we add it in the beginning.
All right. Yeah. Thank you, Professor Naresh.
Okay.
Okay, thank you, Bu Vidya, and thank you, Prof. Naresh. So basically, we should know about the characteristic of our nucleophile.
Yeah.
So yeah, so it can we can know what the mechanism should we use to the carbonyl.
Yeah, because
Okay.
in the next lecture we will look at reaction of alcohol with carbonyl group, and there the protonation is important. Yeah.
Okay. So next week, yeah, maybe. Yeah, Prof. Naresh. Okay, thank you, Prof. So actually we already passed for the past 10 minutes for this season, Prof. Is there any question from student or any from lecturer? Maybe Prof. Asep or
Okay, I have one question
maybe,
from
okay.
Professor Naresh.
Yeah.
I interested with the electronic factor that you
Yeah.
mentioned. You compare between aldehyde and ketone.
Yeah.
Yeah, sometimes we are misconception about that. Yeah, you mentioned alkyl that is refuse the electron.
Yeah.
Yeah. So if the alkyl refuse the electron, will make easier to form the positive charge and negative charge in carbon and oxygen. Could you explain more about the effects? Yeah, the effect, the competitiveness effect between the steric and the electronic factor.
Yeah.
Thank you.
Yeah. So I think if we had a carbocation, if we had a positive charge like that on a carbon, so I'm just going to put an R group here and an R group here and an R group here, right?
Yes.
And say if you have just hydrogen here and hydrogen, say positive charge here, and it has only one, say, R group, and then there's another hydrogen over here, right? So if we are giving electrons in, and giving electrons in, this is going to stabilize the positive charge. It's going to stabilize it, but also reduce the electron or reduce the positive charge that is present on the carbon, right? So here in the beginning, you have a slight positive charge in the carbonyl. There's a slight positive charge and then a slight negative charge. In order to have the reaction, we want more positive charge on the carbon for the nucleophile to attack. If there's more charge here, nucleophile will attack quickly. But if we start reducing the amount of charge that is present in that carbon, then it's going to become less reactive. So that's why having an alkyl group, which is in ketone, you have two groups giving in electrons, you're going to reduce this positive charge. If this positive charge is reduced, then nucleophile will be less reactive because it doesn't have as much positive charge as this one here. So that's why the electronic groups are important. It's different from this carbocations. The carbocations you can stabilize by having alkyl groups. It stabilizes the carbocation because the tertiary carbocation is more stable than, but this is different from the carbocation. We're looking at the reactivity here. And if you got more positive charge, it's going to be more reactive. It's going to be less positive charge, it's going to be less reactive. and the partial positive charge which we are talking about is going to be less in the case of ketone, because there are two groups reducing this charge, partial charge, and if this is reduced, then it's less reactive.
Okay, thank you. Thank you. It's clear. It's clear.
Yeah,
Thank
that's a good observation. It's good point.
Okay.
Okay, all right.
I think we meet the end of this season, Prof. Naresh. We can continue our discussion about the carbonyl next week in Monday. Yeah, in the same time.
Yep.
So thank you very much, Prof. Naresh, for the clear explanation about the carbonyl and carbon as a nucleophile, and then the H as a nucleophile, and also some of reaction in amine. So thank you very much, Prof. Naresh. It's very clear. So and also thank you for all of the participants. And I hope for next week the student will be many of you can ask directly to Prof. Naresh. Is it okay to use bahasa, ya, Prof. Naresh?
Yeah, no problem, no problem.
And you can ask the simple question. Prof. Naresh will answer.
Yeah, that's right. Okay, and then I will bring more questions next week, so we can have more discussion.
Yeah. Thank you very much, Prof. Naresh.
Okay,
so
then.
thank you very much, Prof. Naresh. See you next time. Yeah.
Okay,
and we will end this session. Thank you.
Thank you, Prof. Naresh.
Thank you.
See you on Monday.
Good night. Yeah.
Bye.
Good evening, Prof. Have a rest. Oke, terima kasih Bapak Ibu dan semua mahasiswa. Terima kasih Prof. Asep dan terima kasih Bu Vidya. Terima kasih Bu Gebi masih di sini. Ya, mungkin nanti ya kita akan lanjut di hari Senin ya Bapak dan Ibu dan adik-adik mahasiswa juga di jam yang sama di 14.40 sampai 16.20 ya. Oke. Baik, mungkin akan saya tutup sampai di sini dulu pertemuan hari ini. Semoga apa yang kita diskusikan hari ini bisa bermanfaat buat adik-adik semua dan partisipan juga. Ya, baik, selamat sore dan assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih Bu Amel.
Terima kasih Bu Amel.
Sami-sami.